Swayam Prabha. Digital India. Educated India.
Dear students, I welcome you to the 8th lecture on crystallography, and in this lecture I will talk about the stereographic projection in the part 1, and then I will introduce to you to the concept of crystal forms. Now, if you remember, when we have studied the 32 point groups, I have used the a drawing procedure where the motifs were shown in an horizontal plane in the form of a circle, where the motifs are plotted within the circle, and all the axis of rotation and the mirror planes and center of symmetry are plotted with respect to this circular projection diagram here. And today I will give you a theoretical basis of those projections which we used in that particular 32 point groups here. And I will show you that how this a 3-dimensional crystal can be converted into or would be seen in a 2-dimensional plane here. I will talk about the basic principles of stereographic projection, and I will show you a construction here. Okay. So, let us consider an isometric crystal here, a crystal in the isometric crystal system. This is put within this sphere here, and essentially the stereographic projection is essentially a representation of a 3-dimensional crystal into a 2-dimensional paper. Now, what we have here is that now you have some idea with your knowledge of how a crystal face can be named with Miller index symbol. It will now be very easy for you to appreciate that if this is an isometric crystal system and the crystal belongs to that, then you know that there are 3 crystallographic axes. One of this orientation, that is your A1 axis, this is your A2 axis, and this is your A3 axis. So, you also know that this is a face which is parallel to the A2 axis and is parallel to the A3 axis. So, you will have a Miller index symbol of this face is 100. Same way, this is a face which is parallel to the A3 and parallel to the A1 direction. So, it will have a nomenclature of 0, 1, 0. In the same way, this is the face which is parallel to A2 and parallel to A1. So, it will have a nomenclature of 0, 0, 1. Whereas, you have also a vertical face here. This is the face which is parallel to the vertical A3 axis, and it has intersected the A1 axis and the A2 axis at unit cell lengths. So, then in the position of A3 there will be 0. So, this face can be named as 1, 1, 0. In the same way, if you can have this particular face which intersects the 3 directions A1, A2 and A3 all in their positive directions here, and if the intercepts are all unit cell lengths, then you can have a nomenclature of this crystal face is 1, 1, 1. So, what you can do now is that you can draw a normal to this crystal face here. So, let us consider that for the 100 face, you draw this normal and you allow this normal to intersect the periphery of this sphere. So, that is intersected at this point here. Same way, the normal to 0, 1, 0 intersects the periphery of this sphere at this point here. Whereas, this is the plane, that is 1, 1, 1 plane. If there is a normal drawn on this face and is allowed to project, and it intersects the periphery of this sphere at this place, and this is the 1, 1, 1 position here of this face here. So, this normal are called poles of that face here. Poles, these are normal through the crystal face here. So, what we have done here is that by using the poles, we have converted a two-dimensional plane into a point. That point is essentially in the sphere. So, everywhere all these points, these are face poles with respect to a particular face here. So, this we call it as the spherical projection, and these poles intersect the sphere. As I told you, these planes have now become points, but these points are still three dimensional, because all these points, if you see, they lie at different planes here. So, this is a three dimensional. So, the spherical projection, the poles are still three dimensional. We need to do something by which we can convert these face poles into one particular plane here. What to do? We think of an equatorial plane like this. This plane is this circle here. This circle here divides this sphere into two subspheres here. So, this is the sphere, this is the northern sphere here. If this is the north pole and this is the south pole here, this is the northern hemisphere and this is the southern hemisphere here, and this is this equatorial plane. What you can do here is that you can join. So, let us consider this face fold of plane 1 1 1, you can join this point with the south pole here, because all these face poles lies on the northern hemisphere here. So, you can join all these face poles with the southern hemisphere here and see where it intersects in this horizontal plane here, which is shown this horizontal circle here. So, you see 1 1 1 intersects at this point. You can think of, say for example, Part-1 0 1. So, this is at this point here. So, all these points here, say this is this one here, this is 1 0 1, this intersects here. So, these points, they all now, all these poles, they are at different planes, but all these planes, all these poles that are lying at a three dimensional orientation, they can be converted or they can be projected into this plane by simply joining this point with the south pole here, and the intersection of this line with this circle is essentially that point, which is the stereographic projection of this face fold here. Let us see further here how this can be quantitatively done here. Let us consider there are two face poles, one is of D orientation and other is of E orientation here. Let us consider that these are spherical projections of certain faces. One, this face is 0 1 1 and this is 0 bar 1 1 here, and F G is the projection of the equatorial plane here, and this is a line here, and S is the south pole here. So, what we have to do, the spherical projection of these poles are to be joined with the south pole here. So, these are joined and this intersects this line here, which is the projection of the horizontal plane here. That plane is D dash, this intersection is this point here, that is D dash. So, D in this horizontal plane is now here is D dash, E is E dash. The question is that the position of D dash, that is the stereographic projection of D, where D dash will be with respect to this center and the outer periphery here, that depends on this angle rho. If the angle is 90 degree, then D will coincide with G. whereas when rho is z, then d dash will coincide with O. So, it is essentially then this particular line makes an angle with the vertical. So, this is the north south line here. So, this inclination is important here. So, in order to have the exact position of the stereographic projection of a particular face, you need to know this angle. But you will also know that we need to know another angle here. So, let us have an understanding with respect to this diagram. In this diagram, there are different positions of a of a spherical projection or of a face pole here. Let us consider a face pole of position P. P lies within this vertical plane here. This vertical plane is in this vertical plane and is also lies within the trace of this great circle here. Now, what you have to do to have a stereographic projection of P on this horizontal plane on this circle. So, you have to join P with the south pole here. Now, this is the position of P on this horizontal plane, we call it as P dash. Now, the question is that the position of P dash on this equatorial circle or this horizontal plane, that position is dictated by two angles here. The angle, this angle we have already talked about with the vertical. The other angle is this angle here. This plane is oriented with respect to this east to west direction along at this angle here. So, this is also very nicely determined with respect to this horizontal circle here. If we talk about this horizontal circle here, we have here, if we talk about this reference line here, where let us consider this reference line here is that phi is equal to 0. If we go along this direction here, then what you have here is that this is the direction. So, we have to consider that where we are. So, if we talk about this plane, we have at this angle here. So, let us consider at this angle here. So, from the center of this equatorial circle, if we draw a line here, on this line you will have somewhere P dash position here. So, this P dash is the spherical projection of this face pole P. So, where it will be here, whether it will be here or it will be here or in between O and this S somewhere on this line, that will be dictated by this angle rho. So, this angle rho is essentially this particular distance, this line makes the intersection with this OS line here, this is this OS line here, this is this OS line here. So, this distance we can measure it off here depending on the rho value. This distance is you can make this intersection here. So, this distance you can measure up from the center and this will be the position of P. So, depending on the coordinate of these two angles, the stereographic projection of any plane can be determined here. So, in nutshell then, that using this approach here, all these planes here, they can be projected in this equatorial plane here. And you can also think of an inclined plane here. Let us consider this inclined plane here. There is an inclined plane here. This inclined plane makes when it intersects with this sphere, that intersection is a curved line here. This is the curved line. This is the spherical projection of an inclined plane like this. And when if you want to determine the stereographic projection of this inclined plane, so this each face pole that lies on this curvature, you can now join with the north pole here, that has been done here. So, it has been joined with this point with the north pole here. So, it is intersecting in this horizontal equatorial circle here, this equatorial circle which is the horizontal plane here, and this is the intersection points here. So, these are the stereographic projections of all these spherical projections that lies on this curvature. And ultimately, what you have here, you have this curved line here. This is the stereographic projection of a curved line here. That is very, very important here, that a curved or inclined plane in the when in the stereographic projection, inclined plane will have a curvature, whereas a vertical plane will have an intersection with this horizontal plane here, that will be a straight line here. Okay. So, inclined planes, these are great circles. So, this can be calculated from projected projection, that is calculated from angle rho here. So, great circles on stereographic projection, they are locus of all points that are projected from the intercept of an inclined plane to the equatorial plane that we have just discussed here. Now, these are some of these, we can go back to this particular part here. So, let us consider that there are certain planes here. So, 1 1 1 1 bar 1 bar 1 1 0 0 1 1 1 0 1 1 bar 1 0 0, these are all and lies in one circle here. So, if you say this is 1 0 0, so this is 1 1 bar 1. So, this is one particular great circle where this facefuls will lie, and also you can also think of this particular equatorial circle where they will be in the same plane here 1 0 0, 1 1 0, 0 1 0, bar 1 0 0 and also 0 bar 1 0. So, what we have here is that we can now think of an isometric crystal system where different faces are projected, their stereographic projections are shown here. So, in this particular one here, so let us show the positions of 1 0 0, 1 1 0, this is the 0 1 0 position. And you see something very interesting here. We have studied some time back that if there are two planes they lie in the same zone here, let us consider 1 0 0 and 0 0 1, they lie in the same zone, then using the additive rule you can also find that if this is added 1 plus 0, 0 plus 0, 0 plus 1, that means it becomes 1 0 1, they will also lie in the same zone here. And where will be the position of 1 0 1? In between these 2 points here. So, this is the position of 1 0 1. Similar way, you can also think of the position of 1 1 0 here. And what was that? 1 1 0 lies in between the zone 1 0 0 and 0 1 0 here. So, if you add it up, it becomes 1 1 0. So, this is the position of 1 1 0. And if you add 0 0 1 and 1 1 0, immediately we will find out that 1 1 1 will lie in a zone between 0 0 1 position here and 1 1 0 position here. Similar way, you can think of the position of 0 1 1, bar 1 1 1, bar 1 0 1, 0 bar 1 1, and also you can also find out the position of 1 bar 1 1. So, students, please remember that you are now using certain bar symbol here. You remember this bar symbol refers to the negative direction of the corresponding axis here. So, when you will have bar symbol to the position of the C crystallographic axis, immediately we will be considering that it is intersecting in the negative direction of the C axis here. So, in nutshell then, it will be possible for you to appreciate two important things here. One is this, that the those planes which have an inclined orientation, that is they are not parallel to the vertical crystallographic axis, that is inclined with the vertical crystallographic axis, those planes, the stereographic projections of those planes will be within this circle here. Whereas, vertical faces, their stereographic projections will be on the outer periphery of this circle here. So, you see these all are vertical crystal faces here 1 0 0, 1 1 0, 0 1 0, bar 1 1 0, bar 1 0 0, bar 1 bar 1 0, 0 bar 1 0 and 1 bar 1 0. So, everywhere at the position of C you have 0 here. So, this all these faces are parallel to the vertical axis. So, their positions are in the outer periphery here. Whereas, all these planes which are intersecting the vertical axis here, they will be lying within this circle here, and where this will be lying, that will be dictated by the two angles with respect to the vertical angle, that is rho, and with respect to the horizontal direction, that is phi, that we have discussed here. And in case of an isometric crystal system, let us consider that this is 4 over m bar 3 2 over m, which is the normal class of the isometric crystal system. These are the positions of axis here. So, in case of 4 3 2, we have already shown you when we have generated the 32 crystal classes, particularly the point groups of symmetry corresponding to the isometric crystal system. We have qualitatively shown you the positions of 4-fold axisymmetry, 3-fold axisymmetry and 2-fold axisymmetry. Now, with your knowledge now, it will be possible for you to quantitatively put the position of the 4 triads, and these triads are bar 3 axis here in case of 4 over m bar 3 2 over m, and these are the positions of inclined dyads here, which are edge diagonals here, and this is the position of your horizontal 2-fold axisymmetry. So, they are total 6 in number. This is 1, this is 2, this is 3, this is 4, this is 5 and this is 6 here. And these are the 4 triads, this is 1, 2, 3, 4. And you have 4 3-fold axis of symmetry, one of this orientation, this is horizontal, another of this orientation, this is horizontal, and the vertical will be plotted at the center of this circle here. So, this in nutshell, it gives you a very strong understanding about how different crystal faces can be placed quantitatively, and for our purpose here for the further discussion qualitatively by using the additive and subtractive rule, and at the same zonal symbols here, or same they lie in the same zone. So, we can use additive rule or subtractive rule to place qualitatively the positions of a certain face here. So, this we will apply it in the next lecture that we were studying here. So, in this next part is that we will be studying which is called crystal form here. So, we will be talking about its definition and the common crystal forms in different crystal systems, and we will give in this particular lecture some examples from the isometric crystal system here, and we will also continue in the next lecture further on the isometric crystal forms and in non-isometric crystal forms here. So, what are crystal form? Crystal forms, they are a collection of crystal faces that are related to each other by symmetry. Remember, when we have studied the 32 point groups of symmetry, we have started with a particular motif here, and if you now go back and see the position of motif, all those motifs that we have considered, particularly the open red circle here, this from your knowledge now will have a general symbol of HKL, and that motif, from that motif you have generated through the symmetry elements that are present in that particular point group of symmetry, you have generated other motifs here. And from your knowledge now, all the other motifs are related to each other. This is the concept of crystal form. If you relate that motif in terms of a crystal face, that means all the crystal faces that are linked with one particular face here, which is the general face here, and from that if you can generate all other crystal faces by the operation of the symmetry elements or symmetry operations corresponding to a particular point group of symmetry, then this collection of crystal faces that are related to each other by the operation of symmetry elements, we call this as crystal form. And we generally we take one particular face and we give a general symbol HKL, and to distinguish it from a normal crystal face by putting a second bracket here, and this second bracket will essentially tell you about the form symbol. So, essentially it means that if we know this particular face, from that face it will be possible for us to generate all other crystal faces, all the other faces which are related to this. Now, the number of crystal faces which will define a particular crystal form is a function of two parameters. One is the point group of symmetry that is inherent to that particular crystal form, and the orientation of the face with respect to the symmetry axis. The orientation is essentially is dictated this value of H, K and L. So, these values will tell whether that face is parallel to a vertical axis or it is inclined to all the three axes or of any other orientation. Now, let us talk about the crystal forms that are present in the isometric crystal system. In the isometric crystal system, you know that there are 5 point groups of symmetry. They are 4 over m, bar 3 2 over m, 4 3 2, bar 4 3 m and 2 over m, bar 3 and 2 3. And there are this 1, 2, 3, 4, 5, 6 varieties of crystal forms are possible, and their general symbol is 100, 111, 110, HK0, HHL and HKL. And we will study each form symbol and you will see what are the names of that crystal form and how many crystal faces are related to each other in that crystal form. Let us start with the most simple one here, where we have the form symbol 100, and this form symbol is present in all 5 point groups of symmetry in the isometric crystal system. And in this form symbol, there are 6 crystal faces are related to each other, and they are 100, 010, 001, bar 100, 0 bar 10 and 00 bar 1. I will show you why this is so. So, this is the cube that we have already studied, and you know the 3 general faces 100 is this, 010 is this and 001 is this, and we take this 100 as the general form symbol here. So, let us now study this particular part in some more details. So, name of this form symbol, it is also called cube. In isometric crystal system 100 is called a cube. Now, this is a 6 faced form. This is present in all isometric point groups, and what you have here is that both 4 and 3 or bar 3 axis can relate 100 to 5 other crystal faces here. Now, let us consider with this one here, let us consider that we are considering with a point group of symmetry is where you have here is 4 3 2. So, this is a vertical 4-fold axis symmetry, this is the position, this is a horizontal 4-fold axis, this is another horizontal 4-fold axis, and you have these 4 triads shown by the 4 triangles, and these 4 inclined diodes shown here, and you have also have 2 horizontal diodes here. Let us consider this 100 crystal face, which is the general form symbol of cube. Now, let us consider that you have the position of this threefold axis here. Now, this lines here makes an angle of 60 degree here, 60 degree here, 60 degree here, 60 degree here, 60, 60 here. So, what you have here is that this threefold axis can act upon this 100 phase and can make it coincide at this position here, and this position here is the position of 0 1 0. So, you have a 0 1 0 phase that is generated here, and this phase can again be rotated 120 degree, and this phase comes here, that is becomes 0 0 1 phase here. And same way 0 0 1 phase can be acted upon by this one here, and it can bring this phase here. This is the negative direction of a 1 axis. So, it will have a symbol of bar 1 0 0, and then this threefold axisymmetry can act upon this, and it can be regenerated here. This position is the negative direction of a 2 axis. So, you will have the position here is 0 bar 1 0. Now, what you can also think of is what is your 0 0 1 phase here. 0 0 1 phase is that it is horizontal, it is only intersecting the A 3 axis at the unit cell length of 1 here. Now, you can think of this horizontal two-fold axisymmetry. So, if you think of what will happen if this horizontal two-fold axisymmetry acts upon this 0 0 1, it will rotate 180 degree, and what will happen? This 0 0 1 will, after 180 degree rotation, will come to a position where it will now intersect the negative direction of A 3 axis. So, you will have the form symbol 0 0, this phase symbol, this will be 0 0 bar 1. So, this will be shown at the same position here. So, 0 0 1 and 0 0 bar 1 will be the same position that is shown here. So, what you have now is that this is shown with this x here. So, x represents the 0 0 bar 1, and the yellow circle represents 0 0 1 here, the yellow circle is 1 0 0, etc. So, how many total faces are there? These are 4 here, and these are 2 here on this yellow circle and this cross here. So, these are 6 faces, they are linked with each other, and we call this as crystal form, that is cube. Now, let us come to the next crystal form in the isometric crystal system, and this general symbol is 1 1 0 within second bracket, and this crystal form has been given a name called dodecahedron, and this is this particular a crystal in with this crystal form, that is dodecahedron. Dodecahedron is a 12 faced forms and it is present in all the 5 point groups of symmetry in the isometric crystal system here. And here 4, 3 or bar 3 axis, they will relate 1 1 0 to another 11 rhomb shaped face here. And the mineral where this dodecahedron is best developed is the crystal garnet. So, let us start with one of the point groups of symmetry, that is 4 3 2. So, where will be your 1 1 0 phase here? 1 1 0 phase will be this position here. So, why this is position? Because if this is a position of 1 0 0 and if it is a position of 0 1 0, this is in between will lie this 1 1 0. Question is that where it will lie? It will lie just at the midpoint, because if you draw a 45 degree angle and on this if you join this. So, this will lie intersect on this periphery of this circle, and it will be this position of 1 0 0 1 1 0 sorry. So, if you have this triangle here, this is the triad. What will happen here is that this threefold axis of symmetry will act upon this, and I told you that 120 degree position, this 110 face will come here. Another 120 degree position or rotation, this will come here. Now, what will be the name of this face of this orientation here? So, if you see, this is the position here. In this position, it lies between the center, that is 0 0 1, and this is 0 1 0. So, immediately this face will have a symbol which is 0 1 1. It has intersected the positive direction of the A3 axis here. And what will be the position, or what will be the name of this crystal face which has been positioned here? So, this lies between this face here, which is a symbol of 1 0 0, and this is 0 0 1. So, in between this will be the position is additive rule we apply, it will become 1 0 1. Now, what you have here, from the same way, you know this position now, and you know the position of this triad here. This triad will now act upon this, and this 0 1 1 will now be rotated 120 degree, and it will generate another face here, and this face here lies between this face, that is minus or Part-1 0 0 and 0 1 0. So, it will have a Miller index symbol of Part-1 1 0 here. And what will be this position here? This lies between 0 0 1 and Part-1 0 0. So, it will have a position of Part-1 0 1, and this will again be acted upon by this triad here. So, this will be generated, this face will be generated here, and this will be lying between Part-1 0 0 and 0 Part-1 0. So, it will have a nomenclature of Part-1 0, and the other one, this one will be repeated here, and from here this will come here. And what is this name of this crystal face? This lies between this point here and this face here. This face is 0 0 1, this is 0 Part-1 0. By using the additive rule here, you will have here is that 0 Part-1 1 here. So, this is 0 Part-1 1. So, all this has intersected the positive direction of A3 axis. Now, you have this triad here. So, 0 Part-1 1 will now be acted upon by this triad, and this will be repeated or generated here. So, this phase that comes here, it now lies between 0 Part-1 0 and 1 0 0. So, we will have here is that it will have a symbol of 1 Part-1 0. Now, what you have here? You have now 4 faces here, where 0 is in the position of say A3 axis here. So, there are 4 vertical faces with symbol 1 1 0, Part-1 1 0, Part-1 0, and 1 Part-1 0 here. And up to this stage, we have been able to find out 4 inclined planes here with the symbol 1 0 1, 0 1 1, and Part-1 0 1 and 0 Part-1 1. Now, you have this horizontal two-fold axis symmetry. This horizontal two-fold axis symmetry, this particular face, that is 0 Part-1 1. So, this will be rotated 180 degree, and this will now intersect the negative direction of A3 axis, and that particular face will now be 0 Part-1 Part-1. So, this Part-1 that you see here, that is in the position of A3, the A3 axis, this is means that is intersected the negative direction of A3 axis, and this position I have shown it with this cross here. So, for all this particular inclined planes with respect to the A3 axis, there will be a corresponding inclined plane in the negative direction of this A3 axis. So, I have shown it here with this 0 bar 1 bar 1. I have also it for this bar 1 0 1, there will be a corresponding one bar 1 0 bar 1. For this 1 0 1 1, there will be a corresponding crystal face, that is 0 1 bar 1, and for 1 0 1, you have a corresponding crystal face is 1 0 bar 1. So, you have 4 inclined planes which intersect the positive direction of A3 axis. You have also have 4 inclined planes which intersects the negative direction of A3 axis. So, I have shown this with respect to one circle here, which is the positive direction, and the cross essentially refers to the faces which intersect the negative direction of the A3 axis. So, how many total faces are generated with the starting face 1 1 0? We have now total 4 vertical faces we have discussed, and you have total of 4 into 2 8 inclined faces here. So, 8 plus 4, there are 12 faces here. And you see the beauty of this crystal form here is that if you know the position of one particular face, the positions of 11 other crystal faces become automatically fixed, and all the 12 faces are crystallographically related to each other or symmetrically related to each other. And this is in 432, it is also present in 23, it is also present in 4 over m bar 3 2 over m, it is also present in 2 over m bar 3 and also in bar 4 3 m, and we call this the dodecahedron crystal form here. So, with this I conclude in today's lecture these 2 isometric crystal forms. In the next lecture, I will continue with the remaining isometric crystal forms, and then I will also talk about the non-isometric crystal forms here. Thank you students, we will meet in the next class here. Thank you once again.